A tiny metal sphere beeping in the void ignited a revolution that reshaped our world. We are about to journey through 30 pivotal space events that did far more than advance science. These moments sparked technological revolutions, redefined our place in the cosmos, and altered the very fabric of human history. You will discover the full story behind the triumphs, the tragedies, and the discoveries that forged our modern era. We will uncover how a single photograph changed our view of Earth forever, and why a flawed mirror in space led to one of astronomy's greatest triumphs. What does our drive to explore the stars reveal about us as a species? That faint, rhythmic beep from the heavens was a sound that shattered an era of assumptions. On October 4, 1957, the Soviet Union launched Sputnik 1, a polished metal sphere no bigger than a beach ball, into the cold void of space. Its 4 long antennas transmitted a simple signal back to Earth, a steady pulse that was heard by amateur radio operators across the globe. For many, it was a marvel of science. But for the United States, it was a profound shock, a technological Pearl Harbor that resonated through the halls of power and the living rooms of everyday citizens. The Cold War was no longer a terrestrial standoff. It had just expanded into a new, high frontier. This was not merely a satellite, it was a symbol. If the Soviets could put a sphere in orbit, what was to stop them from putting a nuclear weapon up there, looking down on America from the ultimate high ground? The psychological impact was immediate and immense. Newspapers ran frantic headlines, politicians scrambled for answers, and a deep-seated fear mixed with national embarrassment took hold. The United States, the self-proclaimed leader of the free world and technological innovation, had been beaten. The public gaze turned sharply toward the sky, not with wonder, but with anxiety. This singular event, this beeping sphere, did not just orbit our planet. It launched the space race. The reaction was swift and monumental. Within a year, the United States established the National Aeronautics and Space Administration, or NASA, centralizing its various space efforts under one civilian agency. Almost simultaneously, the Defense Department created the Advanced Research Projects Agency, later known as DARPA, to ensure the nation would never again be caught off guard technologically. The space above our heads was suddenly the new battleground for supremacy, not with weapons, but with rockets and satellites. Sputnik itself was a simple device, weighing about 184 pounds and carrying only basic radio transmitters. But its implications were anything but simple. It proved that humanity could reach beyond its atmosphere, and in doing so, it ignited a firestorm of scientific ambition and geopolitical maneuvering. The world watched as 2 superpowers began a frantic competition that would redefine global politics, accelerate technological progress at a staggering rate, and lay the groundwork for everything from global telecommunications networks to the eyes of orbital espionage. That one small beep echoed far beyond the ionosphere, forever altering the course of history, international relations, and our very relationship with the cosmos. The silent challenge of Sputnik now found a human voice. On April 12, 1961, Soviet cosmonaut Yuri Gagarin was strapped into a spherical cabin named Vostok 1, perched atop a powerful rocket. He was about to become the first human to leave our planet. The risks were almost unimaginable. Scientists were unsure if the human body could even withstand the violent forces of launch, the disorienting weightlessness of orbit, or the searing heat of re-entry. Gagarin was essentially a passenger on a one-way scientific experiment, a testament to human courage in the face of the complete unknown. As his rocket thundered skyward from the Baikonur Cosmodrome, the entire world held its breath. For 108 minutes, he orbited the Earth, a solitary figure witnessing what no one had ever seen before. His voice, crackling over the radio, carried a message of profound awe. "I see Earth," he reported. "It is so beautiful, This was not a statement of politics or competition, but a simple human reaction to the overwhelming sight of our fragile, blue world suspended in the blackness of space. That single observation transcended everything. Back on the ground, his successful return triggered mass celebrations across the Soviet Union and its allied nations. Parades filled the streets, and Gagarin became an instant global celebrity, a living symbol of communist triumph. But in the United States, the mood was one of severe consternation. The Soviets had done it again. They had put a man in orbit, another colossal first that underscored their technological lead. The pressure on NASA and the fledgling American space program became immense, a palpable force demanding a response. This event was far more than a political victory. It was a fundamental breakthrough for all of humanity. Yuri Gagarin had proven that a person could not only survive the rigors of spaceflight, but could work, think, and function in that alien environment. The cosmos was no longer a distant realm for robotic probes alone. It was now a place for people. He personally ignited the dream of interplanetary travel, making the stars feel within our grasp for the very first time. Yet the American response to Gagarin's flight was fraught with setbacks and frustration. Rockets exploded on the launch pad, and suborbital hops felt like small consolation prizes. Then, on February 20th, 1962, the entire nation watched as astronaut John Glenn squeezed into the cramped cabin of a spacecraft he had named Friendship 7. This was not just another launch. It was a test of national will, a chance for the United States to finally match the Soviet feat and orbit the Earth. Millions of people gathered around televisions and radios, their collective hope riding on the Atlas rocket that thundered into the Florida sky. For a few glorious orbits, everything proceeded perfectly. Glenn described the stunning view, the breathtaking sunsets, and the strange, glowing fireflies he saw outside his window. But then, a silent alarm triggered a crisis. A signal from the spacecraft indicated that the heat shield, the crucial barrier that would protect Glenn from incineration during re-entry, might be loose. Without it, Friendship 7 and its pilot would be vaporized in a fireball. Controllers on the ground faced a terrifying dilemma with a global audience listening in. Their solution was as risky as it was brilliant. They decided not to jettison the retrorocket pack, a module normally released after the braking rockets fired. The hope was that the metal straps holding this pack in place would also help secure the potentially loose heat shield during the brutal re-entry. No one knew if it would work. As Friendship 7 plunged back into the atmosphere, a ball of superheated plasma engulfed the capsule, severing communication. For 4 agonizing minutes, there was only silence. The world waited, fearing the worst. Then, a crackle of static, and the welcome voice of John Glenn reporting he was okay. The heat shield had held. The cheers were not just for a safe return, but for a restored sense of American capability. John Glenn became an instant hero, a symbol of cool courage under pressure. His flight proved that the United States was truly in the space race, capable of not just reaching orbit, but of solving life or death problems in real time. It demonstrated that humans could live and work in space for extended periods, gathering vital data and showing the world that sustained spaceflight was possible. This hard-won success paved the way for the next chapter, the 2-person Gemini missions, which would teach NASA how to rendezvous, dock, and walk in space, essential skills for the ultimate goal that was now coming into view. Even as John Glenn's triumph restored American confidence, a far more dangerous drama was unfolding just a few months later, one that would push the world to the very edge of nuclear annihilation. The Cuban Missile Crisis in October of 1962 was a 13-day standoff that made the stakes of the Cold War terrifyingly clear. It was not a space event in the traditional sense, but its resolution would be forever intertwined with the technology orbiting high above. The world watched as American spy planes discovered Soviet nuclear missiles being installed in Cuba, just 90 miles from the United States coastline. For days, the two superpowers engaged in a nerve-wracking game of brinkmanship, with military forces at their highest state of alert. The entire planet held its breath, waiting for a single misstep, a misunderstood order, or a delayed communication to trigger a war that could end civilization. The crisis laid bare a fatal flaw in superpower relations: the agonizingly slow and potentially misinterpreted communication through telegrams and diplomatic channels. In a situation where minutes mattered, the existing system took hours. This terrifying realization, born from the shadow of mutual destruction, forged an urgent need for a direct and immediate line of dialogue. Out of that fear came one of the most critical, yet least glamorous, space-enabled achievements. In 1963, the two nations established the Moscow-Washington hotline. This was not a red telephone as often depicted in movies, but a sophisticated system relying on two primary channels, a constantly open teletype wire and, crucially, a satellite communications link. For the first time, leaders in Washington and Moscow could communicate directly and instantly, bypassing the cumbersome diplomatic machinery that had nearly failed them. This hotline was a direct technological offspring of the space race, utilizing the very satellite infrastructure that the competition had spurred into existence. It transformed global crisis management forever. The ability to send clear, unambiguous messages in real time meant that a future misunderstanding would not have to spiral into catastrophe. The hotline became a silent guardian, a technological safeguard born from the terror of the Cuban Missile Crisis. It underscored a profound truth that while the space race was born from competition, its tools could also become instruments of peace, creating a fragile thread of dialogue that has arguably prevented nuclear war for decades since. That fragile hotline depended on the silent eyes orbiting above, but another set of eyes was about to look down with a different purpose. On April 1, 1960, a rocket carried a strange, drum-shaped object into orbit. It was called TIROS-1, the Television Infrared Observation Satellite, and its mission was to do something no one had ever done: to watch the weather from space. Its technology was primitive by today's standards, equipped with two small television cameras that captured still images of Earth's swirling cloud cover. Yet when those first grainy pictures were transmitted back to Earth, meteorologists were stunned. For the first time in human history, they could see a storm taking shape over the open ocean, far from any ship or weather station. This was a revolution in perception. Before TIROS, forecasting was a ground-level affair, a patchwork of barometer readings, weather balloons, and ship reports that left vast stretches of the planet completely unobserved. Massive weather systems could form and intensify in secrecy, only revealing their full fury as they made landfall. TIROS-1 ended that era of blindness. Over its 78-day lifespan, it sent back more than 22,000 images, each one a priceless piece of a global puzzle. The impact was immediate and profound. For the first time, forecasters could track the birth and movement of hurricanes and typhoons, providing coastal communities with days of advance warning instead of just hours. This new capability did not just improve the accuracy of the 5-day forecast, it began saving countless lives from the very moment those first images were analyzed. Beyond daily weather, TIROS gave us something even more valuable: a global perspective. Scientists could now observe the planet's climate as a single, interconnected system, watching ocean currents, ice formations, and atmospheric patterns on a scale that was previously unimaginable. Those simple black and white photos were the first step toward the sophisticated climate models we rely on today, models that help us understand our changing world. The satellite transformed our relationship with the atmosphere, turning it from an unpredictable force into a system we could begin to comprehend, monitor, and ultimately forecast with a confidence that now underpins global agriculture, transportation, and disaster preparedness. The same technology that watched our weather was now aimed at our nearest planetary neighbor. For centuries, humanity had looked at Mars and seen a world of possibility. Through telescopes, astronomers sketched intricate networks of canals, fueling widespread belief in a dying civilization desperately moving water across a desert planet. Science fiction authors populated it with ancient cities and strange creatures. This was the Mars we knew, a place of romance and mystery, until a small robotic probe named Mariner 4 rewrote the story. Launched in November of 1964, the spacecraft was a technological marvel for its time, a hexagonal bus of instruments and cameras hurtling on a long, silent journey through the interplanetary void. Its mission was audacious: to fly by Mars and capture the first close-up images of another world. The anticipation built for months as it crossed the 216 million-mile gulf. Finally, on July 14, 1965, Mariner 4 slipped behind the red planet and began transmitting its data back to Earth. The signal was agonizingly slow, trickling in line by line over several hours. Scientists at NASA's Jet Propulsion Laboratory watched as the first picture slowly emerged on their monitors, a fragment of the Martian surface from about 6,000 miles away. Then another line and another, gradually assembling a mosaic of gray tones. The initial excitement turned to confusion, then to stunned silence. The Mars they were seeing was not a world of canals and vegetation. It was a desolate, cratered landscape that looked hauntingly familiar and deeply disappointing. It looked exactly like our moon. The images revealed an ancient, geologically dead world, scarred by impacts from asteroids and comets. The atmosphere was far thinner than anyone had predicted, and there were no signs of water, no evidence of the complex canal systems, and certainly no cities. The romantic vision of a living Mars, a vision that had captivated human imagination for generations, evaporated in that single data transmission. Mariner 4's 22 grainy photographs were a cold shower of reality. They forced a profound and painful shift in our cosmic perspective. Mars was not a sister world teeming with life, but a barren and hostile desert. This revelation was a pivotal moment for planetary science. It killed the old dreams, but immediately gave birth to new, more rigorous questions. If Mars was not alive, then what had happened to it? Where did its water go? Did life ever have a chance to begin? The scientific goals for Mars exploration had to be completely rewritten, shifting from a search for intelligent life to a forensic investigation of a dead planet's climate, history, and geology. This single flyby set the stage for every mission that followed, from the Viking landers that would search for microbial life to the rovers that now crawl across its dry riverbeds, all asking the same fundamental question that Mariner 4 first posed. What catastrophic event turned a potentially habitable world into the frozen desert we see today? The stark reality of Mariner 4's dead Mars was a sobering lesson in cosmic humility, but an even more painful lesson was about to be learned much closer to home, not in the void of space, but on the launch pad itself. The Apollo program was racing forward, the goal of landing a man on the moon within the decade, pushing engineers and astronauts to their limits. On January 27, 1967, the crew of Apollo 1, Gus Grissom, Ed White, and Roger Chaffee, were conducting a routine plugs-out test, a simulated launch countdown with their Saturn 1B rocket unfueled and perfectly safe, or so everyone believed. Sealed inside the command module on Pad 34, the atmosphere was 100% oxygen, a design choice meant to simplify the cabin's pressure system. What happened next was swift and horrifying. A stray spark, likely from a damaged wire hidden beneath Grissom's seat, found a perfect fuel source in the oxygen-rich capsule packed with flammable materials like Velcro and nylon netting. In an instant, the interior became an inferno. The intense heat and pressure built up so rapidly that the cabin hull ruptured before the ground crew could even hope to open the complex, inward opening hatch. There was no escape. The transmissions from inside ceased after one final harrowing phrase: "Fire in the cockpit." The three astronauts, all experienced pilots and heroes of the early space program, were gone. The nation was plunged into mourning, and NASA faced its darkest hour. This was not merely a tragic accident. It was a catastrophic failure of design and procedure. The official investigation revealed a deeply flawed culture, one where schedule pressures had allowed known dangers, like the pure oxygen environment and the use of combustible materials, to be overlooked or dismissed as acceptable risks. The Apollo 1 fire became a brutal, necessary catalyst for change. In its aftermath, NASA was forced to halt everything. The command module was completely redesigned from the inside out. The pure oxygen atmosphere was replaced with a much safer two-gas system of oxygen and nitrogen during ground operations. Flammable materials were removed, wiring was thoroughly inspected and shielded, and a new, quick-opening hatch was installed that could be blown open in seconds. More importantly, the agency's entire safety culture was overhauled, with astronauts gaining a greater voice in design decisions and a new, relentless focus on identifying and eliminating potential failures before they could strike again. The ultimate success of the Apollo moon landings was built directly upon the lessons learned from this profound tragedy. The fire, in its terrible way, made the lunar missions possible by forcing a fundamental shift that placed human safety above the relentless drive of a deadline. From the ashes of tragedy, a new kind of courage was forged. By the end of 1968, the pressure was immense. The Soviets were rumored to be planning a manned flight around the moon, and NASA needed a bold stroke to reclaim the momentum. The lunar module, the actual moon lander, was behind schedule and not ready to fly. So, in a breathtaking gamble, NASA decided to change the entire mission. They would send Apollo 8 not just into Earth orbit, but all the way to the moon. For the first time in history, humans would leave the gravitational embrace of their home world, travel 250,000 miles, and slip into orbit around another celestial body. The crew of Frank Borman, Jim Lovell, and Bill Anders were being sent on a journey with no backup plan, no lifeboat. If their main engine failed to slow them down for lunar orbit, they would be stranded, destined to swing past the moon and float endlessly in the void. If it fired too long, they would crash into the barren surface below. On Christmas Eve, 1968, the world watched as the spacecraft emerged from behind the moon and re-established contact. In a live broadcast from lunar orbit, the astronauts began describing the scene outside their windows. They took turns reading from the book of Genesis, sharing a story of creation while gazing down upon a world of profound desolation. And then, something unplanned and magical happened. As their spacecraft rotated, Bill Anders saw it through his window. "Oh my God," he exclaimed, "look at that picture over there. Here's the Earth coming up. Wow, is that pretty?" He scrambled for a camera, loading it with color film, while Frank Borman quipped that he was ruining their planned photo sequence. What Anders captured in that hurried moment became one of the most influential photographs in human history. The Earthrise image. It was not a view anyone had ever seen before. There was the gray, pockmarked, lifeless surface of the moon in the foreground, a stark and absolute desert, and rising above this barren horizon was our own world, a brilliant swirl of blue and white, a vibrant, delicate marble suspended in the infinite black. It was small, and it was alone. That single image did more than any scientific report or political speech ever could. For the first time, we saw ourselves not as citizens of separate nations, but as crew members on a single, fragile spaceship Earth. The picture became the foundational icon for the burgeoning environmental movement, a visceral reminder that our atmosphere is a thin, precious shield, and all of human existence is contained within that tiny sphere. It fostered a profound sense of global unity, a feeling that our shared home was something to be protected, not divided. The vast, empty cosmos in the background underscored our planet's isolation and its incredible, irreplaceable preciousness. Apollo 8 was a triumph of navigation and nerve, but its most enduring legacy was not a technological one. It was a shift in human consciousness, a new perspective gifted to us from 250,000 miles away. That fragile blue marble seen from lunar orbit was now a destination. On July 20, 1969, the lunar module Eagle separated from the command module Columbia, carrying Neil Armstrong and Buzz Aldrin on their final perilous descent. The world held its breath as the two men flew solo, their craft a fragile insect of foil and metal, descending toward a landscape no human had ever touched. But the computers were overloaded, and alarms began to blare. Mission Control in Houston had mere seconds to decide, to determine that the alarms were not critical, and to tell the crew to proceed. Then Armstrong looked out his window and saw the computer's chosen landing site was a treacherous boulder field. With fuel running dangerously low, he took manual control, flying the Eagle horizontally like a helicopter, searching for a safe spot as the countdown to abort echoed in his headset. With less than 30 seconds of fuel remaining, dust finally kicked up and the contact light glowed. "Houston, Tranquility Base here," Armstrong reported, his voice calm. "The Eagle has landed." A collective sigh of relief echoed across the planet. Hours later, as a global television audience of over 600 million people watched, a black and white camera showed a ghostly figure descending the ladder. Neil Armstrong's boot made contact with the fine lunar dust. That's one small step for man, one giant leap for mankind. In that singular moment, President John F. Kennedy's audacious goal, set just 8 years prior, was achieved. The United States had not only caught up in the space race, it had triumphed. The political and symbolic victory was immense, a definitive statement of American technological and organizational prowess during the height of the Cold War. But the achievement transcended geopolitics. The two astronauts planted an American flag, but they also left a plaque signed by the crew and the president, reading, "We came in peace for all mankind." They deployed scientific experiments, collected rocks, and took photographs, proving that this was not just a flags and footprints mission, but the beginning of true extraterrestrial science. For the first time, living beings from Earth were exploring another world, a technological marvel made possible by the collaboration of hundreds of thousands of people. It proved that with immense effort, focus, and collaboration, humanity could literally reach for the stars and touch one. The inspiration from that night ignited a generation of future scientists, engineers, and dreamers, all looking at the moon not as a distant light, but as a place we had been. The triumph of Apollo was a visit to another world, but the next great challenge was learning how to live in the void. That challenge was met on April 19, 1971, when the Soviet Union launched a strange, cylindrical object into orbit. It was called Salyut-1, the world's first space station. This was not a spacecraft designed for quick journeys. It was a home, a laboratory, a prototype for a permanent foothold in the cosmos. Its mission was to prove that humans could not just survive, but truly inhabit space for weeks at a time. The first crew to attempt a docking, aboard Soyuz 10, failed to properly board the station and had to return to Earth. But on June 6th, the three-man crew of Soyuz 11, Georgy Dobrovolsky, Vladislav Volkov, and Viktor Patsayev successfully docked and floated inside. For 23 days, They lived aboard Salyut 1, conducting scientific experiments, observing Earth, and testing the station's systems. They proved that long-duration spaceflight was possible, setting a new endurance record and showing that the human body could adapt, at least for a time, to a weightless environment. Their mission was an unqualified success, a monumental step forward. Then came the journey home. After a perfect undocking and re-entry burn, the Soyuz 11 descent module parachuted to a soft landing on the Kazakh steppe. Recovery crews rushed to open the hatch, eager to congratulate the heroes. But when they looked inside, they found all 3 cosmonauts dead in their seats. There were no signs of a struggle, just a terrible, silent stillness. The investigation revealed a catastrophic and heartbreakingly small failure. A pressure equalization valve had been jolted open prematurely, just seconds after the crew module separated from the service module. At an altitude of over 100 miles, the cabin explosively decompressed. The air, all their breathable oxygen, was sucked out into the vacuum of space in less than a minute. The cosmonauts, who were not wearing pressurized spacesuits, had no chance. They had survived the perils of a weeks-long mission in orbit, only to be lost in the final moments of their return. The tragedy sent shockwaves through the spacefaring world and cast a long shadow over the success of Salyut 1. Yet, the station itself had proven its core purpose. It had demonstrated that a permanent human outpost in space was not just science fiction. The knowledge gained from that 23-day mission was invaluable, providing crucial data on the effects of long-term weightlessness that would inform every space station that followed. The sacrifice of the Soyuz 11 crew led to immediate and drastic changes in spacecraft design, most notably the requirement for all cosmonauts and astronauts to wear pressurized suits during the dynamic phases of launch and re-entry, a safety protocol that has saved countless lives since. Out of this profound loss, the dream of a home in orbit persisted. Salyut 1 paved the way for the American Skylab, the Soviet Mir, and ultimately, the collaborative marvel of the International Space Station. It established the foundational principle that humanity's future in space depended not just on reaching new destinations, but on learning to stay. The dream of a home in orbit was about to give us a new way to see our own. In 1972, a new kind of eye opened in the sky, one that could see the living skin of our planet in a way no human ever had. This was Landsat 1, the first satellite built not to look out at the stars, but to look down at Earth with a scientific, analytical gaze. Its mission was simple yet revolutionary: to systematically photograph the entire planet's land surface, again and again, creating a continuous visual record of a changing world. The technology it carried was its true marvel, a multispectral scanner. This instrument did not just capture pictures in the colors our eyes can see. It observed the planet in multiple wavelengths of light, including infrared and other bands invisible to us. Think of it as giving the Earth a medical scan. A healthy forest reflects light differently than a diseased one. A field with sufficient water looks distinct from a thirsty one. Minerals in rocks, the chlorophyll in crops, the subtle temperature of the ocean, all of these hidden truths were suddenly laid bare in a rainbow of data. This was the birth of modern remote sensing, and it fundamentally rewrote our relationship with the planet. For the first time, we could measure the scale of human impact with undeniable, objective clarity. We could track the relentless creep of deforestation across the Amazon, not from ground-level reports, but with a single, startling image showing a green sea being eaten away by brown scars. Urban sprawl was no longer an abstract concept. It was a measurable, spreading stain of gray concrete across fertile land. Scientists could monitor the health of global agriculture, predicting crop yields and spotting blight before it led to famine. Landsat gave us the ultimate big picture. It provided the first global baseline, a starting point from which all change could be measured. This data became the bedrock of environmental science, and sustainable development. When a volcano erupted or an earthquake struck, Landsat imagery could instantly show the extent of the damage and guide relief efforts. When an oil spill spread across the ocean, its infrared eyes could map the true scope of the slick, hidden from ordinary view. The satellite transformed how we manage Earth's precious resources, from mapping freshwater reserves to locating mineral deposits without ever breaking ground. This unblinking, orbital perspective made it impossible to ignore the fact that we are shaping our world on a planetary scale. It gave us the tools not just to see the changes, but to understand them, and ultimately, to manage our global home with a wisdom that was once impossible. While Landsat was watching over Earth, another spacecraft was being prepared for a journey in the opposite direction, one with no destination and no end. In March of 1972, Pioneer 10 lifted off from Cape Canaveral, its mission to become the first human-made object to travel through the treacherous asteroid belt and fly by the giant planet Jupiter. But its most profound cargo was not a scientific instrument. It was a message. Bolted to the spacecraft's antenna support struts was a small 6 by 9-inch gold anodized aluminum plaque, a cosmic greeting card intended for anyone or anything that might find it millions of years in the future. This was not a casual addition. It was a deliberate, thoughtful attempt to speak to the stars. The plaque was the brainchild of astronomer Carl Sagan and his colleague Frank Drake, who convinced NASA that this historic mission should carry a symbol of its creators. What do you say on behalf of an entire planet? How do you introduce humanity to an intelligence that may not see, hear, or think like us? The design they created was a masterpiece of scientific communication. At its heart are the figures of a man and a woman, drawn to universal scale. The man's hand is raised in a gesture of greeting, a silent hello across the eons. To their left is a schematic diagram of our solar system, showing Pioneer 10's trajectory arcing away from Earth, swinging past Jupiter, and then escaping the solar system entirely. But the most ingenious element is a starburst pattern at the top, a map written in the language of physics. It shows the relative positions and frequencies of 14 pulsars, the spinning cores of dead stars that emit incredibly regular radio signals. These cosmic lighthouses act as a unique coordinate grid, pinpointing the location of our sun and the time of the spacecraft's launch for any civilization advanced enough to understand the map. This small gold plaque transformed Pioneer 10 from a mere probe into a time capsule, a bottle cast into the cosmic ocean. Its launch marked a pivotal moment in our cultural history, the first time humanity consciously reached out to the unknown with a message about ourselves. It was an act of profound optimism, a declaration that we are part of a larger community and wish to make our presence known, yet it also sparked deep questions. Are we representing all of humanity fairly with these two figures? Is it wise to announce our location to a universe we do not fully understand? The plaque forced us to see ourselves not just as inhabitants of a world, but as potential citizens of a galactic neighborhood, forever changing how we envision our place in the cosmos and our responsibility to it. The message aboard Pioneer 10 was a hopeful whisper into the void, but back on Earth, the focus was shifting toward building a more permanent home in that emptiness. Just 1 year after that launch, America's first space station, Skylab, rode a modified Saturn V rocket into orbit. The launch itself was a success, but minutes into the flight, disaster struck. The station's critical meteoroid shield, which also served as a sunshade, ripped away. It tore off one of the two main solar panels entirely and jammed the other, leaving Skylab crippled and overheating. Temperatures inside soared past 130 degrees Fahrenheit, turning the workshop into an uninhabitable oven and threatening to end the entire program before a single crew could board. This was not a planned mission anymore. It was a rescue, the first crew of astronauts, Pete Conrad, Paul Weitz, and Joe Kerwin, launched days later with a singular, urgent goal to save Skylab. They had trained for science, but now they were space mechanics, armed with improvised tools and procedures hastily developed on the ground. Flying their Apollo command module around the stricken station, they saw the devastation firsthand, a tangled mess of metal where a solar panel should have been. Their first attempt to free the jammed array during a spacewalk was a nerve-wracking failure, the astronauts straining with a cable cutter while tethered to their spacecraft, unable to budge the debris. Success came only after a second, even more daring spacewalk. Conrad and Kerwin ventured outside, using brute force to pry the stuck solar panel open. It was a monumental struggle in the frictionless environment, a test of human ingenuity and sheer physical will against the unforgiving reality of space. When the panel finally swung free and deployed its golden wings, the station suddenly had the power it needed to survive. Their heroic repairs transformed a potential billion-dollar failure into a fully functional orbital laboratory. For 28 days, that first crew lived and worked inside Skylab, conducting a marathon of science. They were followed by 2 more crews, each setting new endurance records, with the final mission lasting 84 days. The station's solar telescopes captured unprecedented views of the sun, revealing its violent flares and complex corona in stunning detail. Its cameras monitored Earth's resources, from crop health to pollution patterns. But perhaps its most vital work was studying the astronauts themselves. For the first time, NASA could meticulously document the human body's adaptation to months in microgravity, tracking the loss of bone density and muscle mass, and testing countermeasures to combat these effects. Skylab proved that humans were not just visitors to space. We could be residents. It demonstrated that we could work through crises, perform complex repairs in orbit, and remain productive and healthy for extended periods. The data from those long months became the foundational blueprint for every space station that followed, providing the essential knowledge about living in space that would one day make the International Space Station possible, and paving the way for the even longer journeys to Mars that still lie ahead. That handshake was broadcast across a divided world. On July 17, 1975, an American Apollo command module and a Soviet Soyuz spacecraft gently docked high above the Earth. For 2 days, the 5 astronauts and cosmonauts lived and worked together, sharing meals, conducting joint experiments, and floating between their craft through a specially designed airlock. On the surface, this was a complex technical mission, but for everyone watching, it was something far more profound. It was a handshake in space, a symbol of hope during a period known as détente, a deliberate thaw in the frigid relations of the Cold War. Just a few years earlier, these 2 nations had been on the brink of nuclear war. Now, their most brilliant engineers had collaborated to create a universal docking system, a piece of hardware that was more than just metal and wires. It was a bridge. The technical challenges were immense. The 2 spacecraft spoke completely different languages, both electronically and atmospherically. Apollo used a pure oxygen environment at a low pressure, while Soyuz used an oxygen-nitrogen mix similar to Earth's air at a higher pressure. A direct hatch opening was impossible. It would have been catastrophic. The solution was a magnificent piece of engineering diplomacy, a docking module that acted as a neutral meeting room and a pressure adapter. This module allowed the crews to equalize the atmospheric differences safely, a literal and figurative middle ground where the 2 sides could finally meet. The mission was a resounding success, but its true legacy was not the science performed in orbit. It was the powerful message it sent back to Earth. For the first time, the 2 superpowers were demonstrating that space did not have to be another arena for conflict. It could be a neutral territory, a place where shared curiosity and common challenge overcame political ideology. This single mission planted the seed for an idea that once seemed impossible, that nations could work together to build a permanent outpost in the heavens. The cooperation proven in the void of space laid the essential groundwork for the partnerships that would one day construct the International Space Station, transforming a handshake between rivals into the foundation for humanity's first true home among the stars. A new kind of silence fell over the Martian desert on July 20th, 1976, 7 years after humans walked on the moon. A robotic pioneer named Viking 1 was making its own historic descent. After a year in orbit meticulously mapping the surface for a safe landing site, the spacecraft separated, its lander capsule plunging toward the rust-colored sands of Kryze Planitia. The tension at mission control was absolute. No one knew if the surface would be solid rock or a treacherous, dust-filled quicks, and that would swallow the lander whole. Guided by its automated systems, Viking 1 fired its retro rockets, slowed its descent, and touched down softly on 3 legs. The signal confirming a successful landing sparked jubilation, but the real prize was yet to come. The first image from the surface took several minutes to slowly paint itself, line by line, on the monitors. Scientists and engineers crowded around, waiting for a glimpse of an alien world. What emerged was a stark, breathtaking panorama, a rocky, salmon-hued landscape stretched out under a pale pink sky. The rocks were littered across fine, dusty soil, and the scene was illuminated by a sun that looked strangely familiar, yet utterly foreign. For the first time, humanity was looking at the actual surface of Mars, not through a telescope, but from the ground itself. It was a desolate, yet beautiful, vista that instantly made the red planet a real place. But Viking's true mission was far more ambitious than photography. It was a search for neighbors. The lander was a complete biological laboratory, equipped with 3 ingenious experiments designed to detect microscopic life in the Martian soil. Its robotic arm reached out, scooped up a sample of the rusty soil, and delivered it to the waiting instruments inside. The labeled release experiment almost immediately sent back a stunning result. When a nutrient soup was added to the soil, something in the sample consumed the food and released gaseous waste, just as living microbes would on Earth. The initial data looked like a clear, positive signal for life. The excitement was electric. Had we just found the first evidence of life beyond Earth? But science demands verification. The other 2 experiments told a more confusing and ultimately disappointing story. The gas exchange experiment found no organic molecules, the fundamental building blocks of life, in the soil. The pyrolytic release experiment, designed to see if Martian organisms could incorporate carbon dioxide, also came back negative. The hopeful signal from the first experiment was likely a false positive, a quirk of Martian chemistry. The soil was not teeming with life, but was instead highly oxidizing, filled with peroxides that mimicked biological activity. This was a profound, if sobering, discovery. Mars was not dead, but it was chemically active in a way that was hostile to life as we knew it. Viking's legacy was not a simple answer, but a complex and enduring question. It provided an immense wealth of data about the Martian atmosphere and geology, setting the gold standard for every rover and lander that followed. It taught us that the search for life would be far more subtle and challenging than we had ever imagined, a puzzle that would require new tools and new generations of explorers to solve. While Viking was searching for life in the Martian soil, a much more ambitious journey was just beginning. In the late summer of 1977, 2 robotic emissaries named Voyager 1 and Voyager 2 launched from Earth, beginning the greatest voyage of exploration in human history. Their mission was a grand tour, a once-in-an-eons opportunity made possible by a rare alignment of the outer planets. This celestial geometry, which occurs only once every 176 years, allowed the 2 spacecraft to use the gravity of each giant world as a slingshot, hurling them on to the next with minimal fuel. They were our eyes and ears on an unprecedented tour of the solar system's distant giants. What they found there was nothing short of revolutionary. Voyager 1 revealed Jupiter not as a placate gas ball, but as a storm-racked, dynamic world, home to a raging anticyclone 3 times the size of Earth, the Great Red Spot. But its most stunning discovery was on Jupiter's moon Io, where it spotted erupting volcanoes, the first active volcanism ever seen beyond Earth. This tiny moon was alive, its surface constantly remade by powerful eruptions driven by the immense gravitational tug-of-war between Jupiter and its other moons. When the Voyagers reached Saturn, they transformed its rings from simple bands into a breathtakingly complex structure. The images revealed thousands of individual ringlets, braids, and spokes, a cosmic vinyl record of unimaginable scale. They discovered new moons, including ones that seemed to shepherd the ring particles, their gravity carving out gaps and shaping the dazzling disk. Voyager 1 used Saturn's gravity to sling itself out of the solar system, but Voyager 2 continued the grand tour, becoming the first and only spacecraft to visit the ice giants, Uranus and Neptune. At Uranus, it found a world tilted on its side, with a bizarre magnetic field and a collection of dark, icy moons. Then, at the system's final stop, Neptune, it revealed a world of deep, supersonic winds and a massive, Earth-sized storm dubbed the Great Dark Spot. There, it found its final marvel, Triton. This frozen moon was geologically active, with nitrogen geysers erupting from its surface, spaying dark material miles into its thin atmosphere. The Voyager missions fundamentally rewrote every textbook on our solar system. The outer planets were no longer distant, featureless points of light. They were revealed as unique, complex families of worlds, each with its own wild weather, intricate ring systems, and collections of bizarre, active moons. The mission taught us that our cosmic neighborhood is a place of constant change and violent beauty, a gallery of planetary wonders that we had only just begun to appreciate. That promise of routine access to space became a roaring reality on April 12, 1981. With a thunderous rumble that shook the Florida coast, the Space Shuttle Columbia, a vehicle that looked more like an airplane than a traditional rocket, climbed into the sky on a pillar of fire and smoke. But this was not just another launch. Strapped to the orbiter's back were 2 giant, reusable solid rocket boosters, and beneath it hung a massive, disposable fuel tank. This complex stack was the world's first reusable spacecraft, a revolutionary machine designed to launch like a rocket, but land on a runway like a glider. For the first 2 minutes of its maiden voyage, the entire assembly ascended together. Then, the spent solid rocket boosters were jettisoned, parachuting into the ocean to be recovered, refurbished, and flown again. The orbiter, with astronauts John Young and Bob Crippen at the controls, continued its climb into orbit using its own main engines. For 2 days, they tested the spacecraft systems in what was essentially a high-stakes shakedown cruise. The most critical test came during re-entry. Columbia had to bleed off its immense orbital speed by plunging into the upper atmosphere, its belly protected by thousands of revolutionary silica thermal tiles that glowed white-hot under the intense friction. After surviving this fiery trial, it transitioned from a spacecraft into a glider, and Young guided the unpowered vehicle to a perfect touchdown on a dry lake bed in California. The entire concept had worked. This was the dawn of the shuttle era, a paradigm shift in how we thought about space travel. For 30 years, the shuttle fleet became America's workhorse, a versatile space truck that fundamentally changed the economics and operations of spaceflight. Its large cargo bay and robotic arm made it the perfect platform for deploying massive satellites, from communications relays to top-secret military payloads. But its capabilities went far beyond simple delivery. It could also capture, repair, and redeploy satellites, a feat dramatically proven with the rescue of the stranded Solar Maximum Mission satellite, and later, the Hubble Space Telescope. Without the shuttle's ability to rendezvous, grapple, and allow astronauts to perform complex spacewalks, fixing Hubble's flawed vision would have been impossible. The shuttle's cabin became a unique laboratory with the addition of Spacelab, a pressurized module built by the European Space Agency. Inside, crews conducted thousands of experiments in microgravity, advancing our knowledge in medicine, material science, and fluid physics. The program was not without its profound tragedies, but its legacy is undeniable. It trained a generation of astronauts in the art of orbital operations, honing the skills of rendezvous and spacewalking that would be essential for building the International Space Station. By demonstrating that a spacecraft could be reused, the shuttle broke the cycle of one-time use rockets and made the dream of a permanent human presence in space a practical, achievable goal. A flawless eye in the heavens promised to unveil the deepest secrets of the cosmos. The Hubble Space Telescope, launched aboard the Space Shuttle Discovery in April of 1990, represented the pinnacle of astronomical ambition. For decades, astronomers had dreamed of a telescope above the distorting veil of Earth's atmosphere, one that could see the universe with crystal clarity. The expectations were astronomical, quite literally. Then, the first images came down. Instead of sharp points of light, the stars were blurry, surrounded by hazy halos. The devastating truth was soon revealed. Hubble's primary mirror, painstakingly ground to perfection, suffered from a microscopic flaw known as spherical aberration. The edge of the mirror was too flat by a mere 1/50th the width of a human hair, a manufacturing error of heartbreaking precision. This tiny defect meant the telescope could not focus properly. The $2.5 billion observatory, the most complex scientific instrument ever placed in orbit, was nearly blind. The despair within the scientific community was profound. Hubble became a punchline, a symbol of government waste and technological hubris. But in that moment of crisis, a different kind of genius emerged. Engineers and scientists devised a radical correction, not by replacing the mirror, but by giving the telescope a pair of glasses. The first servicing mission, in December of 1993, was one of the most complex and daring spacewalks ever attempted. Over 5 tense days, spacewalking astronauts performed what amounted to orbital brain surgery. They replaced Hubble's camera and installed a set of new instruments, including COSTAR, the Corrective Optics Space Telescope Axial Replacement. This ingenious device contained a series of coin-sized mirrors that precisely counteracted the flaw in the primary mirror, bending the blurry light into a perfect focus. The world held its breath as the first corrected images were transmitted. The result was an unqualified triumph. The stars were now sharp, brilliant pinpricks against the black velvet of space. Hubble could finally see, and what it saw would rewrite our cosmic story. It turned its gaze to a stellar nursery in the Eagle Nebula and returned an image that would become iconic: the pillars of creation. Those towering columns of cold gas and dust, illuminated by the fierce light of newborn stars, were not just beautiful, they were a detailed lesson in the violent, creative process of star formation. Then, astronomers pointed Hubble at what appeared to be a tiny, empty patch of sky, a dark void between the stars. For 10 days, it gathered every single photon of light, and the result was the Hubble Deep Field. That single image revealed not emptiness, but a universe teeming with thousands of galaxies, each a swirling island of billions of stars, reaching back to the very dawn of cosmic time. It was a humbling census of the cosmos, proving that galaxies were everywhere we looked. Hubble's most profound discovery, however, was one we could not even see. By meticulously observing distant supernovae, The telescope helped astronomers measure the rate of the universe's expansion. They expected to find that the pull of gravity was slowing this expansion down. Instead, they found the opposite. The expansion of the universe was accelerating, speeding up over time. This shocking revelation pointed to the existence of a mysterious, repulsive force permeating the fabric of space itself, a force we now call dark energy. This one discovery fundamentally altered our understanding of cosmology, of the universe's ultimate fate. Hubble did not just give us pretty pictures, it gave us data that pinned down the age of the universe to about 13.8 billion years, confirmed the existence of supermassive black holes at the hearts of galaxies, and provided an unprecedented window into the evolution of the cosmos. It transformed from a symbol of failure into the most productive scientific instrument ever built, all because humans had the courage to fly up and fix what they had broken. For 15 years, Mir was a lone, battered fortress in the sky, a symbol of Soviet endurance that outlasted the very nation that built it. When the station was finally guided to a fiery end in the remote South Pacific on March 23, 2001, it was not a failure, but a carefully choreographed final act. Its descent was a spectacle of engineering precision, a controlled burn that sent glowing fragments streaking across the atmosphere before plunging into the ocean depths. This was the first time a structure of such immense size and complexity was deliberately brought home, a necessary demonstration for a future cluttered with orbital outposts. Mir's legacy was forged not in its peaceful end, but in its turbulent life. It was a place of incredible triumph and terrifying peril. Cosmonauts endured a dramatic fire that filled the modules with toxic smoke, a nerve-shredding collision with a resupply ship that punctured a module and sent the station into a slow spin, and perpetual financial struggles that threatened to shut off the lights for good. Yet through every crisis, the crews persevered, patching holes, restoring power, and proving that human ingenuity could keep a home in space alive against staggering odds. It was aboard Mir that humanity truly learned what it meant to live in space for the long haul. Valery Polyakov spent an uninterrupted 14 continuous months there, a record that still stands, demonstrating that the human body could withstand the journey to Mars and back. The station was a relentless teacher, its every malfunction a harsh lesson in orbital mechanics, life support, and psychological resilience. Its controlled destruction was perhaps its most vital lesson of all, proving that we must take responsibility for the structures we leave in orbit. The safe disposal of Mir set the critical precedent for the eventual, inevitable retirement of the International Space Station, ensuring that our greatest achievements in space do not become deadly hazards for the generations who will follow us into the cosmos. A new kind of explorer rolled onto the Martian surface in the summer of 1997. After a 7-month journey, the Mars Pathfinder spacecraft did not make a gentle, powered descent. Instead, it slammed directly into the thin Martian atmosphere at over 16,000 miles per hour, protected by a heat shield, a parachute deployed to slow its violent fall. But in the final moments, the most audacious part of the plan unfolded. Giant airbags inflated around the lander, surrounding it in a protective cocoon. It was dropped from 60 feet up, and then it bounced, not just once, but over a dozen times, a gigantic beach ball careening across the rocky terrain before finally coming to a rest. When the airbags deflated, the lander opened its petals like a metallic flower, and a new era of planetary exploration began. Nestled inside was Sojourner, a tiny, 6-wheeled rover no bigger than a microwave oven. It rolled cautiously down a ramp onto the rust-colored soil, becoming the first robotic vehicle to roam another world. The public was captivated. This was not a distant, abstract mission. It was a daily adventure. NASA made all the images and data available on the brand new World Wide Web, and millions of people logged on to see where Sojourner was exploring each day. They watched as the little rover, named for civil rights advocate Sojourner Truth, used its alpha proton X-ray spectrometer to nudge rocks, analyzing their chemical composition and beaming the results back to Earth. The mission was a triumph of a new philosophy at NASA: faster, better, cheaper. It proved that you did not need a billion-dollar, decade-long project to do groundbreaking science. The airbag landing system was a spectacular success, demonstrating a low-cost, robust method for delivering payloads to the surface, and the rover itself was the real revelation. Why stare at one spot when you could drive over to the interesting rock? Sojourner's success paved the way for an entire dynasty of Martian rovers. It proved the concept of mobility, a lesson that directly enabled the twin rovers' Spirit and Opportunity, which would cover miles of terrain, and the car-sized laboratory's Curiosity and Perseverance, which now search for ancient signs of life. Pathfinder and its tiny rover did more than just explore a small patch of Mars. They opened the door for everyone on Earth to ride along, transforming space exploration from a government secret into a shared human experience. That tiny rover on Mars was a symbol of our growing reach, but a far grander project was taking shape much closer to home, high above the planet, in the vacuum of low Earth orbit. The first piece of a new world was being maneuvered into place. On November 20, 1998, a Russian Proton rocket lifted off from the Baikonur Cosmodrome, carrying a module called Zarya, which means sunrise. This unpressurized, autonomous cylinder was the seed from which the International Space Station would grow. Just weeks later, the Space Shuttle Endeavour rendezvoused with Zarya, its crew using the robotic arm to gently attach the American-built Unity node. For the first time, the two core segments of the station were connected, a literal and symbolic handshake between former Cold War rivals in the silent expanse of space. This was not merely another satellite launch. It was the beginning of the most ambitious engineering project ever attempted, a football field-sized laboratory that would be constructed piece by piece, module by module, over the course of more than a decade. The political and logistical challenges were staggering. The station was a joint venture between the United States, Russia, Canada, Japan, and 11 nations of the European Space Agency. These were partners with different languages, different engineering standards, and a complex history of competition and suspicion. How do you design a bolt that fits both American and Russian tools? How do you create a common computer language for a station whose modules were built on opposite sides of the world? Every wire, every pipe, every software line had to be meticulously negotiated and integrated. The construction itself was a high-stakes ballet performed in microgravity. Over 37 shuttle flights and countless Russian launches, new modules were delivered like puzzle pieces. Astronauts and cosmonauts conducted more than 160 spacewalks, often lasting 6 or 7 hours, to connect power cables, install radiators, and bolt new laboratories onto the growing structure. They were essentially building a skyscraper while floating next to it, using robotic arms as giant cranes and tethers to keep from drifting away. The result of this unprecedented collaboration is more than just a scientific outpost. It is a permanent human presence in the cosmos. For over 2 decades, the station has been continuously occupied, a testament to what humanity can achieve when we work together. Inside its modules, a unique microgravity environment allows for research impossible on Earth. Scientists grow perfect protein crystals to develop new medicines, study the strange behavior of fluids to create more efficient engines, and observe the long-term effects of spaceflight on the human body, gathering the essential data we will need for the 3-year journey to Mars. The International Space Station is a promise, a prototype for the future homes we may one day build on the Moon, on Mars, and beyond. The sky itself seemed to weep fire over Texas. On the morning of February 1st, 2003, the Space Shuttle Columbia was minutes from home, gliding through the upper layers of the atmosphere after a successful 16-day science mission. But as the orbiter streaked across the southwestern United States, it began to break apart. To the horror of those watching from the ground, the familiar white speck trailing a plume of smoke fractured into multiple pieces, scattering debris across 2 states. There were no survivors. The 7 astronauts aboard, a crew of scientists, engineers, and pilots, were gone. The tragedy was not a sudden explosion, but a slow, terrible unraveling that had been set in motion 16 days earlier, during the very launch that had cheered them into orbit. During ascent, a briefcase-sized piece of foam insulation had broken away from the giant external fuel tank. It struck the leading edge of Columbia's left wing at over 500 miles per hour. At the time, engineers on the ground saw the impact on launch video and grew concerned, requesting clearer imagery of the damage from military satellites. But their requests were denied by NASA management, who had become accustomed to foam shedding over the shuttle's 22 years of flight. It was viewed as a maintenance issue, not a fatal flaw. This time, it was catastrophic. The foam strike had punched a hole in the reinforced carbon-carbon panel that shielded the wing from the searing heat of re-entry. As Columbia began its descent, superheated plasma, reaching temperatures of 3,000 degrees, seeped into the breach. It melted the aluminum structure of the wing from the inside out, destroying the shuttle's ability to fly and leading to its violent disintegration. The Columbia Accident Investigation Board delivered a scathing report that echoed the painful lessons of the Challenger disaster 17 years prior. It cited a broken safety culture at NASA, where schedule pressure and a desire to maintain launch tempo had once again led to the normalization of deviance, where known risks were accepted until they resulted in catastrophe. The loss forced the agency to confront a devastating truth. The shuttle, for all its revolutionary capabilities, was an inherently fragile and risky vehicle. It grounded the entire fleet for over 2 years and directly led to the decision to retire the program once the International Space Station was complete. This tragedy fundamentally reshaped America's entire approach to human spaceflight. The era of relying on a single, government-owned spacecraft was over. NASA turned its focus to the next chapter, outsourcing routine travel to low Earth orbit to commercial companies like SpaceX and Boeing through the Commercial Crew Program. This shift allowed the agency to redirect its own resources and engineering might toward a more ambitious goal, a return to the moon. The lessons carved from Columbia's loss became the bedrock for the new Artemis program, a mission built on a foundation of unprecedented safety, international partnership, and a renewed vow to honor the sacrifice of those who gave their lives to push humanity farther into the cosmos. The stark reality of a Martian desert was forever altered by a robotic geologist digging in the Arctic plains. In 2008, NASA's Phoenix lander arrived at a deceptively flat region near the planet's North Pole, a place where the sun never rose high in the pink sky. Its mission was not to roam, but to stay, to use its robotic arm like a backhoe and dig into the strange, polygonal patterns in the soil. Scientists believed this terrain might hold frozen water just beneath the surface, but belief was not proof. For weeks, the arm scraped and scooped, revealing a hard, white substance just inches down. At first, the team thought it might be a layer of salt, but when they took a second look at the trench a few days later, the white material was gone. It had simply vanished into the thin, cold air. This was the smoking gun. The substance wasn't salt. It was water ice, and it had undergone a process called sublimation, turning directly from solid ice into water vapor without ever becoming a liquid. The lander's own instruments confirmed it, tasting the soil and detecting the chemical signature of water vapor. This was a monumental confirmation, Mars was not a uniformly dry world. It was a world with its water frozen into the very ground, a vast, subsurface reservoir preserved at its poles and likely elsewhere. The discovery was a complete game-changer in the search for life. Where there is water, there is at least the potential for life as we know it. Phoenix proved that the essential ingredient for biology was not just a memory locked in ancient rocks, but a tangible, accessible resource on Mars today. This single finding immediately redirected the entire strategy for exploring the Red Planet. Future missions, like the Curiosity and Perseverance rovers, would no longer be sent to random, interesting locations. They would be targeted with precision to areas where orbital data showed evidence of past water flows or subsurface ice deposits, places where the ghosts of ancient Martian life were most likely to be preserved. For the dream of human settlement, the implications were staggering. Astronauts could not possibly carry all the water they would need for a long-term stay. Phoenix showed them that they might instead become pioneers, learning to live off the land by mining the Martian ice for drinking water, breathable oxygen, and even rocket fuel. The mission transformed our view of Mars from a dead relic into a world with a wet, active history and a frozen, but potentially useful, present, fundamentally raising the stakes for every robot and every human who will one day follow its tracks. Our galaxy holds more worlds than anyone dared to dream. For centuries, we wondered if planets around other stars were rare, a special circumstance of our own solar system. Then, in March of 2009, a telescope named Kepler launched on a singular quest to stare at one patch of sky and answer a simple, profound question: how common are Earth-like planets? Its method was brilliantly simple: watching for the tiny, periodic dimming of a star's light. This is the transit method. Imagine a firefly flying in front of a distant searchlight, a minuscule dip in brilliance almost impossible to detect from trillions of miles away. Kepler was designed to measure these microscopic winks, the telltale signature of a planet crossing the face of its sun. For 9 years, it monitored over 150,000 stars in the constellations Cygnus and Lyra, its unblinking eye gathering a torrent of data. The results were staggering. Kepler revealed a cosmos teeming with planets. They are not the exception, they are the rule. The data suggests that, on average, every star you see in the night sky has at least one world orbiting it. This translates to billions of planets in our Milky Way galaxy alone. The diversity was just as breathtaking. The telescope found a menagerie of alien worlds, from puffy gas giants larger than Jupiter to rocky planets orbiting their stars in less than a single Earth day. But the true revolution came from the discovery of planets in the Goldilocks zone, the habitable zone where temperatures could allow liquid water to pool on a rocky surface. Kepler found thousands of these worlds, planets with the right size and the right orbit to potentially harbor the chemistry of life. This single mission fundamentally rewrote our cosmic address. We are not living in a special, privileged solar system. We are one among countless billions. The existence of life elsewhere shifted from a philosophical question to a statistical probability. The sheer number of Earth-like planets makes the universe feel profoundly more spacious and deeply more lonely, or perhaps filled with untold possibilities. Kepler's legacy ignited a new golden age of exoplanet science, fueling the development of powerful new telescopes that will one day analyze the atmospheres of these distant worlds, searching for the chemical fingerprints of a living biosphere. The roar of a rocket engine echoed not from a government launch complex, but from a tiny, remote atoll in the Pacific. This was not NASA or the Russian space agency at work. It was a small, privately funded company called SpaceX, and its rocket was the Falcon 1. For years, the company, led by entrepreneur Elon Musk, had been battling against the odds. Their first 3 launches ended in failure. each one a fiery explosion that brought the company to the brink of bankruptcy. The pressure was existential. If the fourth launch failed, there would be no fifth. Everything rested on this one flight. On September 28, 2008, that fourth Falcon 1 rocket lifted off from Omelek Island. The team watched, their hearts in their throats, as it climbed higher and higher. This time, there was no explosion, no sudden loss of signal. The rocket's second stage engine fired perfectly, pushing a dummy payload into a stable orbit around the Earth. Cheers and tears of relief erupted in the control room. They had done it. This was not just another successful launch. It was a revolution. For the first time in history, a privately developed, liquid-fueled rocket had reached orbit. The significance of that achievement is almost impossible to overstate. For 50 years, access to space had been the exclusive, enormously expensive domain of a handful of superpower governments. The barriers to entry were colossal, requiring national treasuries and massive industrial bases. SpaceX, with its shoestring budget and relentless focus on efficiency, shattered that monopoly. They proved that a commercial company could not only build a rocket, but could do it for a fraction of the traditional cost. This single success heralded the dawn of the commercial space age. It ignited a fundamental shift in the economics of spaceflight. The old model was like commissioning a custom-built ocean liner for every single voyage. The new model, pioneered by SpaceX and the companies that followed, was about building a reliable, reusable freighter. This new philosophy of driving down costs and increasing launch frequency has since unlocked entire new industries that were once the stuff of science fiction. It enabled the development of massive satellite constellations like Starlink, which aims to blanket the globe in internet access. It opened the door for private space stations, orbital manufacturing, and the burgeoning market for space tourism, where civilians can now purchase a ticket to experience the overview effect for themselves. The success of Falcon 1 did not just put a payload in orbit, it put the entire future of humanity in space onto a new, radically different trajectory. A silent, car-sized laboratory was plummeting toward the red planet at 13,000 miles per hour. For the team at NASA Jet Propulsion Laboratory, the 7 minutes between the spacecraft hitting the Martian atmosphere and its hoped-for landing were known as the 7 minutes of terror. Everything had to happen with split-second, automated precision, because a radio signal from Earth would take 14 minutes to reach Mars. By the time they heard the spacecraft had entered the atmosphere, it would already be alive on the surface, or a smoldering crater. The sequence was a masterpiece of engineering audacity. A heat shield weathered temperatures of 2,000 degrees Fahrenheit, a supersonic parachute, the largest ever deployed on another world, billowed open to slow the descent. But the 1-ton Curiosity rover was too heavy for airbags. The final stage was something out of science fiction. A rocket-powered sky crane ignited, hovering 60 feet above the surface. It then lowered the rover on 3 nylon tethers, like a massive mechanical spider lowering its precious egg. The moment Curiosity's wheels touched dirt, the tethers were severed, and the sky crane flew away to crash at a safe distance. The control room exploded in a catharsis of cheers and tears. They had pulled off the most complex landing in the history of robotic exploration. Curiosity's mission was the next logical and most profound step in the Martian saga. Following the water discovered by Phoenix, this rover was a mobile geochemistry lab sent to Gale Crater to answer the ultimate question: could Mars have ever supported life? It was not looking for life itself, but for the environmental ingredients that would have made microscopic life possible, a habitable environment. For years, the rover trundled across the crater floor, its laser zapping rocks and its drill chewing into the ancient bedrock. The data it sent back was a revelation. Curiosity discovered streambeds where water once flowed knee-deep, and it analyzed clay minerals that can only form in fresh, neutral water. the kind of water you could have drunk. The rover was essentially driving across the dried-up floor of an ancient lake that existed for millions of years. Then came the clincher. Drilling into these 3 billion-year-old mudstones, Curiosity found preserved organic molecules, the carbon-based building blocks of life. This was not evidence of life, but it was the preserved pantry, the complex chemistry needed for life to get started. The narrative of Mars was transformed forever. This was not a planet that was always a barren desert. Billions of years ago, it was a world with a thick atmosphere, with persistent lakes and rivers, with all the necessary ingredients for life to have emerged. Curiosity proved that early Mars was not just habitable, it was genuinely Earth-like. This discovery shifted the fundamental question from, was Mars habitable, to the even more tantalizing one, did life ever actually call this ancient, watery world home? Deep within the frozen archives of the solar system, a relic from its violent birth was waiting to tell its story. The European Space Agency's Rosetta mission spent a decade in a cosmic chase, slingshotting around Earth and Mars to match speed with a tumbling mountain of ice and rock known as Comet 67P, Churyumov-Gerasimenko. When Rosetta finally arrived in 2014, it revealed a world unlike any we had ever seen. The comet was not a simple, round snowball, but a bizarre, rubber duck-shaped object with dramatic cliffs, deep pits, and a surface darker than coal. For months, Rosetta mapped this strange terrain from orbit, searching for a place to send its precious cargo, the 100-kilogram Philae lander. The chosen site was far from ideal, a relatively flat area littered with boulders and cracks, but it was the best chance they had. The release of Philae was a tense, autonomous maneuver, a gentle push into the comet's minuscule gravity. For 7 hours, the lander drifted silently toward the surface. Then the signal arrived. Philae had touched down, but the celebration was short-lived. The lander's harpoon system, designed to fire and anchor it to the soft surface, had failed. Philae bounced. It soared back up, tumbling for nearly 2 hours in the feeble gravity before touching down again, only to bounce once more, a final, smaller hop that sent it careening into a dark crevice. When it finally came to rest, Philae was tilted on its side, its legs in the air, and its solar panels mostly in shadow. It was stranded, yet against all odds, the little lander began its work. With only 60 hours of battery life, its instruments sprang to life, drilling into the comet's surface and sniffing the thin atmosphere. The data it sent back, alongside Rosetta's continued observations from orbit, was nothing short of revolutionary. They discovered that the comet's water had a different isotopic signature than Earth's oceans, challenging the long-held idea that comets alone delivered our water. More importantly, they found a rich soup of complex organic molecules, including the amino acid glycine, which is a fundamental building block of proteins. Philae's imperfect, bouncy landing had given us our first direct taste of a comet, and it tasted of life itself. This mission fundamentally linked these icy wanderers to our own origins. While they may not have filled our oceans, they very likely seeded the early Earth with the probiotic chemistry, the raw ingredients that eventually sparked life on our planet. We are, in a very real sense, children of the cosmos, and missions like Rosetta help us read the recipe written in the stars. A subtle shiver passed through the cosmos on September 14, 2015. It was not a ripple of light or a burst of radio noise, but a literal tremor in the fabric of spacetime itself. After traveling for more than 1 billion years, this faint vibration, produced by the collision of two massive black holes, finally reached Earth. It stretched and squeezed our entire planet by a distance smaller than the width of a single proton, and two colossal instruments, the Laser Interferometer Gravitational Wave Observatories, or LIGO, were listening. This was the first direct detection of gravitational waves, a confirmation of a prediction Albert Einstein made 100 years earlier. He theorized that massive accelerating objects, like orbiting black holes, would create waves that travel at the speed of light, warping the very geometry of the universe. Proving it required a level of precision that bordered on the impossible. The LIGO observatories are essentially the most sensitive rulers ever built. Each consists of two 4-kilometer-long vacuum tubes arranged in an L shape. A laser beam is split and sent down each arm, bouncing off mirrors to travel back and forth. In normal conditions, the light waves return and cancel each other out. But when a gravitational wave passes through, it minutely changes the length of one arm relative to the other by 1/10,000th the diameter of a proton. This microscopic change allows a tiny flicker of laser light to pass through, signaling a detection. For decades, scientists worked to isolate these instruments from every conceivable disturbance, from rumbling trucks miles away to the subtle noise of microscopic cracks forming in the mirror coatings. The detection was not just a triumphant checkmark for Einstein's theory. It was the opening of an entirely new sense for astronomy. For all of human history, we have studied the universe by observing light, from visible rays to radio waves and X-rays. But now we could hear it. This first signal was a cosmic chirp, the final few moments as two black holes, each dozens of times more massive than our Sun, spiraled into each other and merged into a single, more massive object. In that cataclysm, a portion of their combined mass was converted into pure energy, radiated away as these gravitational waves. This was an event completely invisible to traditional telescopes, a dark collision in a dark void. With this new sense, we can now perceive the most violent events in the universe, the mergers of neutron stars, the explosive deaths of massive stars, and the ripples from the Big Bang itself. We are no longer just stargazers. We are now listening to the symphony of spacetime, hearing the hidden music of the cosmos for the very first time. For more than a century, black holes existed only as mathematical monsters in the pages of theoretical physics, cosmic phantoms whose gravitational pull was so intense that not even light could escape. We inferred their presence from the frantic dance of stars around an invisible center, but seeing one directly was considered impossible by its very definition. How do you take a picture of an object that consumes light? The answer arrived on April 10, 2019, not from a single powerful telescope, but from a virtual instrument as large as the Earth itself. This was the Event Horizon Telescope, a global collaboration that synchronized 8 radio observatories from the high deserts of Chile to the frozen peaks of Hawaii, creating a planet-sized dish to peer into the heart of a galaxy 55 million light-years away. The target was the supermassive black hole at the core of galaxy M87, a behemoth with a mass of 6.5 billion suns. The challenge was not just distance, but time. The swirling, superheated gas and dust falling into the black hole changes its appearance minute by minute. To capture a coherent image, every single telescope in the global array had to observe the exact same photons at the exact same moment, a feat of atomic clock precision that required perfectly clear weather at every site simultaneously. For days, the team waited for this celestial alignment, their entire year of planning hinging on a brief window of cooperative skies across the entire globe. When the data was finally collected, the real work began. The observations generated a staggering amount of information, so much that it could not be sent over the internet. The hard drives, filled with petabytes of raw data, had to be physically flown to central processing centers in the United States and Germany. For 2 years, teams of scientists worked to calibrate, clean, and synthesize this mountain of information, using complex algorithms to essentially develop a photograph from a camera the size of our world. The result was a shimmering, fiery ring of orange and yellow, a perfect circle of light surrounding a profound and perfect darkness at its center. This was the black hole's shadow, the point of no return. The bright ring is not the black hole itself, but the photon sphere, the final orbit where light is bent into a circular path by the immense gravity, a last glimpse of illumination before it plunges into the abyss. The central darkness is the event horizon, the one-way door out of our universe. This single image did more than just make the invisible visible. It was a direct test of Einstein's theory of general relativity under the most extreme conditions imaginable, and the theory passed with flying colors. The size and shape of the shadow matched the predictions with stunning accuracy, confirming our understanding of space-time warped by colossal mass. Beyond the science, the picture became an instant cultural touchstone, a symbol of human curiosity and our relentless drive to understand the cosmos. It proved that through unprecedented international cooperation and technological ingenuity, we could unveil the universe's deepest secrets, transforming a theoretical abstraction into a tangible and beautiful reality. We had finally seen the unseeable. A new era of exploration landed with a gentle thud in the dusty stillness of Jezero Crater. On February 18, 2021, NASA Perseverance rover, the most advanced robotic laboratory ever sent to another world, completed its own flawless 7 minutes of terror. Its mission was singular and profound: to hunt for the fossilized remains of ancient microbial life. It did not target just any location, but an ancient river delta, a place where, billions of years ago, water once flowed into a vast lake, depositing sediments and, just possibly, preserving the chemical whispers of biology. Perseverance was not merely a geologist, it was an astrobiologist and a curator. Its core objective was to drill and collect dozens of pencil-thin rock and soil samples, sealing them in ultra-clean tubes and leaving them in a strategic cache on the surface. This was the first step in an audacious, multi-mission plan known as Mars Sample Return, a grand endeavor to bring these pristine pieces of Mars back to Earth, where scientists in fully equipped labs could search for signs of life with tools far too large to send on a rover. But before the rover began its primary work, it had to deploy a small stowaway. Tucked beneath its belly was Ingenuity, a tiny 4-pound helicopter with 2 carbon fiber rotors. The idea was considered almost ludicrous. The Martian atmosphere is only 1% as dense as Earth's, offering almost no air for rotors to push against. Could powered, controlled flight even be possible on another world? On April 19th, after being dropped onto the surface, Ingenuity spun its rotors to an astonishing 2,500 revolutions per minute and lifted off. It climbed to a height of 10 feet, hovered, turned, and then landed. The entire flight lasted 39 seconds, but it was a lifetime of achievement. For the first time in history, a vehicle built by humans had achieved powered, controlled flight on another planet. That short hop was a Wright brothers moment for interplanetary aviation. Ingenuity proved that drones could become the scouts of the future, flying ahead of rovers to map out safe paths, survey scientifically interesting terrain from above, and reach areas like cliff faces and crater rims that are utterly inaccessible to wheeled vehicles. It transformed our concept of exploring other worlds from a ground-level crawl into a 3-dimensional survey. Together, Perseverance and its aerial companion represent the pinnacle of our search for answers. One roams the dried-up riverbeds, using its suite of instruments to analyze rocks for biosignatures, the chemical traces left by living organisms. The other soars above, providing a bird's-eye view of the geological story written into the landscape. This partnership is not just about collecting rocks, it is about building a case, piece by piece, for the most profound question we can ask: are we alone in the universe? The samples Perseverance gathers are the evidence for that trial, and Ingenuity has shown us we now have the tools to be both the detective and the judge. From that first faint beep to the fiery ring of a black hole, these 30 events are more than just milestones. They are the story of humanity reaching beyond its grasp, a chain reaction of discovery where each breakthrough built upon the last, pushing the boundaries of what we thought was possible. A satellite launched in competition gave us the global communication networks that now bind our world together. A telescope's flawed vision, when corrected by human hands, revealed an accelerating universe and our own cosmic insignificance. A simple weather eye in the sky taught us to track storms and monitor the vital signs of our own planet, while a rover digging in the red soil transformed Mars from a distant light into a world with a wet, possibly living, past. These are not abstract achievements locked away in laboratories. They are woven into the very fabric of your day, from the GPS that guides your travel to the satellite imagery that forecasts your weather and the global perspective that reminds us of our shared responsibility for this fragile blue marble. The journey does not end here. It is an ongoing story, one that relies on our collective curiosity and support. The next chapter, the next event that will forever alter history, is being written right now in laboratories, launch control centers, and the minds of a new generation of explorers. What will it be? The first boot prints on Mars, the discovery of a biosignature in an exoplanet's atmosphere, or something we have not yet even dared to imagine? Let us know in the comments which of these cosmic moments resonated most with you, and subscribe to continue this incredible journey through the final frontier.